Yeah, so I talked to Paul a little earlier, and he was saying that this workshop has shown how much scope expansion there is and mission creep. Because you start with sparse linear algebra, and then you have databases and all sort of stuff. So I'm going to try to mission creep as much as I possibly can. You can consider this talk just a summary of everything that's been going on, because I think everything I'm going to say has been anticipated a little bit in different talks. So this is, I'm going to try to talk about where I think we're going, whether we want to or not. There's a bunch of different applications that we care about, and most of these have been talked about already. You have different domains like computational engineering, and you have machine learning and bio and all sorts of stuff. And we do not want to build, we do not want our languages that we will use to run across different machines to be bound to each of these domains. There's too many domains, so we want to lay it at a lower level. Excuse me, I'm also a little jet lagged. So what can we do if we can't build a domain-specific language for every domain? What can we do? Well, all of the things that we're going to be running on large computers and across heavy accelerators are going to compute on collections of data. And why collections of data? Well, that's where the parallelism is. It's sort of like why do you rob banks? That's where the money is. So we're going to be dealing with collections of data. And there's fewer collections of data than there are application domains. So here's a few collections. You have sets, you have relations like we talked about, you have graphs, you have meshes, and you have tensors and things like that. So in addition to many different types of collections, you also have many different types of hardware, and these are all domain-specific accelerators, including some that are now cropping up into normal machines like GPUs. And all of those accelerators are also working on collections of data, whether it's small tensors, small vectors, or larger pieces of data like a sparse tensor in the case of maybe the Semanova hardware. So we have collections that we want to compute with. We have hardware that can compute on collections. And then we have many different data structures as we've seen. It's not just dense arrays. You have the KD trees that Jayon mentioned. You have B trees. You have hash maps. You have all sorts of tries and sparse matrix data structures. So we have a lot of different data. We have a lot of different types of data structures. So we end up with a bunch of applications and a bunch of hardware and a bunch of data structures. So how can we get on top of this so we don't have to write 50 different domain-specific languages and 50 different compilers? So we need programming systems, but not too many of them. So the reason why we need compilers is because they're a productivity tool. They're not a performance tool. We can always write the code they generate. They're productivity tools that let us generate the code we need as opposed to write it by hand. And if we're going to have a comprehensive programming system that can deal with different applications, then I really mean all the applications that we're going to run on supercomputers, not just a few domains. Then we need a small number of high-level languages on which we can write those applications. It can't be 50 languages. That's going to be unwieldy. We need a modular compiler infrastructure where we can have the same compiler infrastructure work on different types of languages in this small family and also be portable across all the different architectures I just saw. Not just CPUs and GPUs, but also data flow architectures, specialized TPUs and systolic arrays, and distributed machines. So we need to be able to plug in hardware as we build different hardware, and we need to be able to plug in different data structures, as we've seen. And then we need to be able to generate code that iterates over different data structures, composes different hardware, so you can use the different hardware resources you have available to you. And then you want it to be able to fuse and tile for locality. Locality is key here. And by fusion, I mean fusion across, not just inside one of the languages, but across the languages, which means we have to have a unified compiler infrastructure that all of the languages can feed into. So let's look at what the small number of languages are. And I think the guiding principle here is that we're dealing with collections of data. So when object-oriented programming came out, the basic idea was that we were going to have objects that are each a recursion on the machine. Each object, you implement each object independently, and then you get emergent behavior as the objects are communicating with each other. We want the opposite of that. We want a collection of objects where we define the global behavior, whether it's a tensor equation or some sort of physical laws. And then we want the local behavior of the different objects to be compiled from the global descriptions. So this is a different programming model than object orientation. It's a collection-oriented programming model. And luckily, we have some precursors. Here's a few of my favorite papers. The settled paper from Kennedy and Schwartz that dealt with a set language. And the basic idea was if you could detach the computations from the order in which you iterate over data and the way you access data, you can create a portable programming system. The same idea in relational algebra at about the same time. And then there's a wonderful survey by Blalock and his student on collection-oriented languages. And these are good starting points, but we need something that's a little bit more semantically rich than just these. So here are the 4 languages. They're just languages on different types of collections. So first is the relations, and relational algebra is really good for combining data to form a system. And by system, I mean a system of interconnected objects. A relation, by definition, is a relation over sets. So it's relationships between sets. Next are graphs. So graphs are good for thinking about local operations. You want to forget about the whole and focus on a piece. Maybe you want to do a mesh cut, or you want to do some sort of local triangle stiffness computation. So very good for local operations. Tensors are good for the opposite. They're good for global operations, where you want to forget about the pieces, shove everything into a large tensor, and think about the whole system as one particle moving in very high-dimensional space. And then we want space, which is good for spatial operations, where you're talking about not. So the first one is how do objects relate to a relation. The next one is how do they relate to edges that are themselves objects. Then you have tensors, how do they linearly relate, where the different dimensions of the tensors are sets of objects. And space are how do objects relate through spatial distances with some sort of distance metric in some sort of space. And I think these are complete enough that you can do most of the computations we're going to do on large computers. And these also accidentally sort of hit all the 4 major areas of mathematics. So that's probably not a coincidence. Okay, so let me go through quickly what kind of operations we want on different ones. They're all going to be collection-oriented operations where the operations do not talk about the order of operations or how we access data. Because if you talk about them in your programming model, you cannot port your code without untangling those details. We cannot program with respect to the machine even. So if you write code with respect to one machine, we have to untangle it to port it to a new machine. So you're going to write code with respect to collections of data. So you have the tensor algebra on tensors. You have nonlinear functions like you find in machine learning, but also general functions, foo, applied across different tensors. Stencils, you want to be able to reshape tensors, where it's kind of the typecasting operations of tensor, where you compose them together or reshape them into a different dimensional tensor and so forth. And you want recurrences. This recurrence here is the Cholesky decomposition, which is the direct solver. That's very common. It's just a recurrence through different tensors. And if those tensors are sparse, you have a sparse Cholesky. Then you have relations. And relations, they're the most complete, probably, of these, where you just want relational algebra. So here you see the different operations we've seen before today. And here's the triangle query expressed in relations. And then for graphs, you really want local operations where you can zoom in on a piece of the graph and just do a local operation there. And you probably do that for all vertices at the same time in parallel. But you want more general graphs. You want hypergraphs, and you want graphs where edges are themselves objects that can be connected by other sets that are also edges. So you can get hierarchies, like a cell connects faces, connects edges, connects degrees of freedom. So you can get meaningful hierarchies like that. So here, for instance, you have a tetrahedra where you have a hyper edge there that connects multiple vertices. So that way you can model meshes with just graphs. And here the same thing is shown, where you have faces connecting edges, connecting vertices. And that would be a triangle in a mesh. Okay, and then finally the spatial operations. They have to do with how objects relate through space. So here are some objects scattered around in space, and maybe you want to do a range query like in a spatial database. Or maybe you want to express a collision detection because you're implementing a simulation. Here's collision detection in a small functional language. And here's ray tracing in a functional language. This is ray tracing, that line. So you can express them very compactly if you have a good language. Of course, these are not optimized. That has to happen by the compiler. You have to have data structures underneath this that accelerates all of this. So you want these 4 collections, so you want ways to move between them, because an application is not just going to be a mesh. It's going to be a mesh plus linear algebra, for instance. There's going to be multiple different abstractions in the same application, and you need ways to move between them in the programming model, and then you need a compiler that can remove the cost of those transitions, so you don't actually move data. Just because you translated a graph into a matrix doesn't mean you have to actually move any data. You can just push that linear algebra back onto the graph, for instance. Here's a couple of examples. So this is a relation here that turns into a matrix. So 2 of the columns turn into dimensions, and the last column turn into the values of the matrix. Here you have a piece of a simulation application where you have a hypergraph that describes a mesh that turns into a matrix. You compute on the matrix to maybe compute some dynamic simulation, and then you project that back onto the mesh, which is a graph. And then if you the type system here relates triangles and the degrees of freedom to the types of the tensors. So that's the relationship between the different data models. They're all dealing with sets. Everything are sets. And then here you have, I've taken the same simulation and I added collision detection, where you add a couple of matrices that model the collisions, and then you have 2 colliding dolphins at the nose there, and they add into the linear system, and then you can compute with that. So you get 3 different data models in the same application very naturally. You don't want 4 compilers, and you don't want this to be too complicated. So you want all of these languages to be compiled down to one unified intermediate representation where you have a single language. And that's possible because everything here is dealing with sets and iteration of the data structure, and obviously so, because when you have collections, you iterate over data structures. What else would you do? So it's all about iterating over sets and bags and iterating over relationships between sets and bags means multisets. So for instance, a tensor is just a linear relationship between different sets. A relation is a relation over sets, so it's a relationship over sets. And space is just relationships between the objects themselves through space. And then graphs are just connected by edges, so also just relationships between vertices. So that means that we can start to think about all of these as some hierarchical traversal through different sets that are connected in some way, whether it's through a relation or through a matrix or through a graph. So here you see the sets on this tensor getting turned into a one of these coordinate hierarchies. And then we can have loops that just run over the different sets. So triply nested loop, and if there's multiple different data structure, we can do co-iteration with known techniques. Same with the relation, same kind of hierarchy. Same with the graphs, same kind of hierarchy. And then these get a little wild. The object in space, the trees there end up being space-filling trees, like KD trees and things like that. So whereas these will be 3 nested loops, these are going to be some sort of recursion over a space-filling tree, like a bounded volume hierarchy. But still, we are iterating over sets and collections of sets and the relationships between sets. So I think it's possible to build such a compiler where we can take the different operations, put them all together into one compiler infrastructure that has a very general IR that's just about iterating over sets. And then when you have that IR that iterates over sets and relationships between sets, we can compile that down to specific code that iterates over specific data structure. So the IR will be abstracted from the specific data structures, and then you can embed that as you compile down to low-level hardware. And I think it's possible to make that portable across all the major architectures. We've seen in our research how to compile the sparse tensor algebra to CPUs, GPUs, distributed machines, data flow hardware, and also to TPU-like hardware. So I think that's possible for the other people have shown the same with relational algebra, and I think it's possible with the rest too, of course. So that's my talk. Thanks.
Awesome, thank you, Fred. It looks like we have one question from Matthias. If somebody else has a question, I will go with them in preference. Sorry, Matthias. Olivia, Fred's your advisor. You can ask him later. Okay. Let me get a question from Tobias real quick. And could everybody who is a speaker in the session make their way up to the front here so that we can do the panel?
So I saw at the end you made the case that I mean everything is sets and backs, right? So there should be this universal abstraction, right?
Yeah. Yep.
And so I'm wondering a little bit like what we've seen in other compilers is that you really tailor abstraction to specific use cases. Mm-hmm. I'm wondering is there some kind of tension where you say actually like sometimes the same concept looked from a different perspective is more. Make certain transformations easier, make certain mappings better. So how do you work with this tension?
Well, I think at least for graphs and tensors and relations, they look very similar when you get them down to sort of abstract loops over sets like that. So you can tile all of them, and you can do those kind of transformations. Where I think they become a little different is that, say in tensor algebra, you can make some assumptions because they live in a semi-ring, whereas in relational algebra, it's more general, so you can't make those assumptions. But I think from the point of view of what can you express and how can you optimize it, I think that's very similar. I think mechanically, I think the search space is very different. So I can imagine the specific programs will look very different depending on where they come from, and you might need different optimization algorithms to search over that.
So you say there's a global minimum in terms of like a global optimum in terms of how to represent these things versus potentially multiple choices.
Yeah, I think
okay.
there's a way to get them in such a way that it's not just the union of three things, but it's a more unified thing.
Mm-hmm.
Yeah.
Okay.